Okay, we are on chapter 16. We are working with covalent bonding. We just finished with ionic bonding between a metal and a nonmetal, or cations and anions when there's a transfer of electrons. Covalent bonding, remember, occurs between nonmetals only, creates a molecular bond or molecular compound, and electrons are shared. Now we're going to start with what they call a single covalent bond. And a single covalent bond means they share one pair. And each atom donates an electron, or contributes. Each atom contributes one electron. It's pretty easy to see where this is going to come from if you take a look at their dot structure. So let's look at hydrogen. Okay, hydrogen has one dot. To be full, it would need a second dot to be like helium. And this is part of the reason why when hydrogen comes together, it will come together very easily with another hydrogen. What's going to happen are these electrons right here are going to share. And by sharing that pair, they will have a full outer shell. So there's your shared pair. That is a dot structure of a covalent compound. And that's why we see hydrogen is H2. That shared pair indicates a single bond. Another way that you can draw this, instead of using a dot structure, you could write it using a structural formula. A structural formula will represent a shared pair with a line. Oops, spelled that wrong. All right. Let's do another example where you see a single bond. Let's look at fluorine. We know fluorine is also diatomic. If you look at its original structure, it has 7 valence electrons, and you can see it needs one more right there to have its 8. So it will react with another fluorine right here. And so what's going to happen is here's where they're going to share. And so when we write the dot structure, there's your shared pair, and then you continue to fill the rest of the dots in. Okay, so again, shared pair, and if you write it as structural, you're still going to have your lone pair of electrons there. The structural only replaces the shared pair with a line. Both hydrogen and fluorine are diatomic, but this again does occur in all molecular compounds. So let's take a look at water. We know water is H2O. Take a look at their dot structures. If you have hydrogen, it has one dot. And remember, there are 2 of these. And then you get oxygen. Oxygen has 6. And you can see oxygen needs 2 more electrons. So what's going to happen is this will come here, and it will share there, and this one will come here and share there. So you'll have your oxygen, and then in comes a hydrogen to share right there, and one to share right here. If you were to draw it as a structural formula, you would have the lone dots on your oxygen and a line between your hydrogen and oxygen to show the shared pair. Now we're going to take a look at a more difficult structure, and that's with double bonds. If you have a double covalent bond, it's just a little more complicated because you have 2 shared pairs. Okay, 2 shared pairs. Oxygen is a great example of this. Oxygen gas in its elemental state. So oxygen, once again, has 6 valence electrons. It needs 2 more to have its 8. And if we draw another oxygen, it needs 2. So what's going to happen? It can share this, and if it just shared once, it'd be a single bond, but it would still be 1 short. So here's your other one. Now how would we draw this? You take your oxygens, you've got your lone pairs. Whoops, that one shouldn't be there. and then these two will be drawn in the middle. Okay, that is your double bond. Two shared pairs. Okay. If you draw that as a structural, you would show two lines and still show the lone pair. So don't forget, the dots around are known as lone pairs. Sometimes they are called, instead of lone pairs, unshared pairs is another name for that. Okay. And then another example could be a triple bond. By now you could probably guess what a triple bond would be. The triple bond would have three shared pairs. A good example of that is nitrogen. Nitrogen has 5 valence electrons. It needs 3 more. So when you bring in 2 nitrogens with their 5 electrons, they each need 3. So here's 1, there's 2, and right here would be a third one. So when we draw this, you'd have your 3 shared pairs in the middle, and then a lone pair or unshared pair on the end, on the top. It doesn't matter where you place it. Okay? If you draw this as structural, you'll have 3 lines and then your lone pairs. Now that you've seen single, double, and triple bond, and you know to use the dot structures, you can start predicting how these are going to arrange, what their dot structures will be for any kind of compound. So let's take a look at carbon dioxide. How will they come together? Again, the first thing you're going to do is you're going to look at your carbon. And we had talked about bonding capacity before. Carbon has a maximum bonding capacity of 4. It could bond with 4 things. But in this instance, it only wants to bond with 2. So we need to see how it is going to bond with 2. Now, since this has 4 for a bonding capacity, and oxygen only has 2 for a bonding capacity, the one with the highest bonding capacity tends to be what we call a central atom. So I know that this oxygen will bond to this, and this oxygen will bond to this. I just have to figure out how they are going to bond. All right, so since I know carbon is in the center, I just have to figure out how these are going to come together. Now, you can kind of see, remember our oxygen needs 2 more, so I can kind of see that these 2 would want to come together, and that would leave 2 more for this oxygen. So that's what I'm going to do. I'm going to take these dots here from carbon, and I'll put 2 here, and I'll put 2 here, and then 1 oxygen here. 1, 2, 3, 4, 5, 6, and here 1, 2, 3, 4, 5, 6. And that doesn't work. Okay? So why doesn't that work? Well, if you count how many dots there are, I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Here, I've got 6 and 6 is 12 plus 4 is 16. That doesn't match. Oh, it does match. Take that back. Let's try this again. One of the things that I did not do correctly, and again, it's going to take practice just like me here. I don't get everyone right the first time. So let me start this again. What I like to do, and I was trying not to do this because it was messy, but I'm going to put an oxygen on each side. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Again, I know it's messy, but if I don't do this, I mess it up, as you just saw. So, we all make mistakes. So, those 2 will bond, and those 2 will bond. Okay, so when I write this again, that's a double bond. I have 2 from my carbon, 2 from my oxygen. And then I'll have 2 lone pairs. Okay. I don't need these electrons to get 8 around carbon, so they're not used. They just stay that way. And then I can see here and here that those are going to come together. That's a double bond between the oxygen and the carbon, and then I still have 2 lone pairs for the oxygen. Again, these take time, these take practice. Like I said, I always draw these even though they're messy, okay? Because you can always just redraw the structure. Now, this one is your dot structure, and if I went to structural, I could show my shared pairs with lines, and then just put my dots on there. And again, the dots don't have to be perfectly around there as long as you show that they are paired together. Again, it's going to take practice. So in this one, 2 double bonds. This is considered one of the harder ones, the more challenging structures to draw. All right. Now there's something that we call a coordinate covalent bond. This can be very confusing, so keep that in mind. It's not the easiest thing to draw. All right, so this is shown between carbon and oxygen, carbon monoxide. Okay. Again, carbon needs 4 more electrons to have its 8, and oxygen only needs 2 more. Okay, so how is that going to work? Well, it looks like this and this one could bond, and this one and this one could bond. Okay, and then that would give me C, double bond, O, and then 2 single electrons here, which could pair up, which wouldn't be a big deal. And it looks like this would be okay. But something that we haven't talked about is that, remember, every atom is trying to get 8 valence electrons in their dot structure. The only exception to that would be hydrogen, because it only needs 2. And then there's a couple more exceptions that we'll talk about. So let's go back up to carbon dioxide. If I were to circle oxygen right here, count how many dots are there. 2, 4, 6, 8. Perfect. Then I look at this one, because remember, they're sharing these. 2, 4, 6, 8. Perfect. Then I look at my carbon. 2, 4, 6, 8. Perfect. Through sharing, they all have 8 valence electrons. That's not working here. If I look at my oxygen, 2, 4, 6, 8, that's great. But I come over here and I have 2, 4, 6. That's not good. That's not acceptable. That's not stable. That's not what's going to happen. Carbon needs 2 more. So if I take this structure and say, how can I rearrange these electrons in such a way that they'll have 8? Well, carbon only has 6. Carbon is the one that needs more. So you look over at oxygen and it has 2 pairs that it's not doing anything with. So what's going to happen is this is going to come here, and our structure is now going to look like this, a triple bond. Now if we recount this, 2, 4, 6, 8, carbon now has 8, and when you look at this, 2, 4, 6, 8, oxygen still has 8. So we end up with a triple bond. Now this is what we call a coordinate covalent bond. One atom donates a pair to share. Now this only happens when there are not enough electrons around one of the atoms and another atom has a pair that it can share. All right, that's all the time we have for this lesson. So when I come back, I will show you how to draw dot structures for polyatomic ions. Polyatomic ions have a charge and they're made up of nonmetals, so they also show covalent bonding, and those are a little more complex, so we will come back to those. In the meantime, you have some worksheets that you can practice with.